Now let's consider why that approximation, although it was plenty accurate for the small deflection, wouldn't be accurate for larger deflection. Our 30 centimeters is now going to be replaced by delta x, which is significantly larger compared to L. In this case, we see that the 30 centimeters is not even a part of a triangle with angle theta up here. The only triangle we have with the angle theta would be this triangle here. And that the 30 centimeters would actually be this side of this triangle. Now we could, to determine the angle theta, go to a lot of trouble. Okay, we've got a triangle down here, which can be broken by doing a diagonal into two triangles. We got an angle here which is equal to this angle here, alternate interior angles for a transversal between two parallel lines. This angle here will then be equal to this angle here, and this angle will be complementary to this angle. We can then begin setting up simultaneous equations for these angles, and we could actually follow this scheme and determine the angle. It would be a mess, and it's hard to figure out, it's hard to think of. Or we can simply note that this side is L and this side is our delta x, which we presumably know, and that this side divided by this side is just the sine of theta, so that the sine of theta is delta x over L, and we can easily find theta that way. In fact, given this information, to find this distance here, we don't even have to use sines and cosines. We could simply use the Pythagorean theorem. The distance from here to here is the square of L minus the square of our delta x.